We have our lab one report here. Constant velocity car thingamabob. Uh, Intro, we had a car. It went and yeah, that was really great. We just pushed it somewhat constant velocity. Then we coded a simulation that is just an orb that is at the same constant velocity. There is no surroundings unless you count me pushing the car, but really we're just observing the car as it already has a constant velocity, and that would be the system. We used two equations here. I recorded the video, after I record the video, use the tracking software to find the position over time. And then I used this wonderful uh, initial position and final position formula, subtracting initial position from final position, dividing that by time, average velocity, and then I put that in the coding for a formula. It's like initial position plus velocity times time is final position. So that was really nifty. That was great. Uh, Fun photos. We got the photos of the little car on the little track with the little ruler. And then we got some code, which is me setting the ball's initial position to the initial position according to the tracking software to make sure everything lined up properly. And then we got the code, um, and also the velocity that we found using the average formula. And then we have all the coding math. I didn't really write all this. This came preloaded, I believe. And, the time is the time that it took for the car to travel, 0.866 seconds. We have the little demonstration of what happened when I ran the code. And then we have our graph. This is the two plotted against each other. The orange is the code, the blue is the car. As you notice, they're not the same. You might ask yourself, why aren't they the same? Please tell me my next slide is errors. It is. The next slide is errors, which is why aren't they the same? We got some friction and the tracking software, right? Friction means the car's velocity wasn't actually constant. RIP. That's why it hits the little like buoy and then slows down, I think. But most importantly, tracking software. When I click the dots for the position of the car for each frame, I wasn't 100% accurate, and that caused some problems. That would be our sources of error as to why the graphs aren't identical. So for our questions, our first question is asking when you analyze your video in the tracker, you made the choice of orientation. And what would happen if we were to flip the axes? If we were to flip the axes, like what are we observing? If we were measuring like the Y or Z axis opposed to the X that we were measuring, there wouldn't be any change at all because we're only moving along the one axis. And if we were to flip the positive and negative of the x-axis, that would simply invert the sign of our slope, thus making the position go down over time instead of up over time. And as for our observations being predicted by our computational model and how we could tell how many pushes or pulls were being added together to give a zero net force in our actual car, we didn't actually have a constant velocity car, so we just pushed it. And so the friction over time did reduce the velocity, so there was not a net zero force. But if there was a constant velocity car, it would be pretty simple to say the friction and air resistance versus the force of the engine motor of the car. So that would be the way we would answer those two questions.